Hello, thanks for coming. It's nice to have an audience. I'm going to talk about where's mathematics going. In fact, that's going to be the end bit where mathematics, I've got you here under false pretenses, because what I'm actually going to, I'll spend the first half of the talk setting the scene, where mathematics is and what's happening in the world of technology that makes me think that, what might affect mathematics, and then we'll finish with where's mathematics going. And by mathematics, I should say, I mean mathematics is a very broad thing, but what I'm really talking about is research, modern mathematical research is what I mean by mathematics in this talk. So before we start, I've just got one preliminary slide before we start. So firstly, thank you very much to the Simons Foundation for this opportunity to speak. It's a terrific opportunity. And I should say that my background is that I did 20 plus years doing curiosity-driven research in algebraic number theory in the Langlands program. And then in 2017, I had some kind of midlife crisis. Is really a fair way of describing it. I had some kind of midlife crisis, and I started looking at what I perceived, what I thought mathematics was and what I thought it could be. And I got sort of quite unhappy with the state of things. And I sort of stepped away from it a little bit and started wondering whether somehow technology could fix some of my worries. And that's sort of the context that you should sort of understand this. You can frame this talk in that there's this fact here. I had some kind of panic attack 8 years ago, and now here I am. So let's get going. We'll start with where mathematics is now. So what does mathematics look like now? And mathematics started in lots of different places, but historically, let's choose one of the random places. We could do Euclid's Elements. So Euclid's Elements starts book 1 with 5 common notions and 5 postulates. Nowadays, we would call these things axioms. And then from these axioms, Euclid started making logical deductions. And by the end of book 1, it proved Pythagoras' theorem. And then there's kind of 12 more books after that. And the way it works is that every time you put sort of these facts together and made another deduction, you can put that deduction on your pile of things that you're now allowed to assume. And you can go on from there. So that's, in a sense, that's one place where it started. And it turns out that this was a sufficiently interesting idea that we just kept doing that. And so we're still doing that. In about the 1880s, we changed the axioms a bit. Euclid's axioms were sort of applied to geometry. We wrote down some axioms that sort of covered all of mathematics. And then we started building from these axioms, and we built and we built and we built. And a consequence of that is that mathematics is now incomprehensibly large. We're a long way. It may be in the late 1800s, there were people that sort of understood all mathematics, but now it's absolutely out of the question. So that's what we've managed to do as human beings. We've built this gigantic edifice called mathematics, and there it is. So let's try and understand what it looks like. So at the beginning, Euclid, he wrote down his ideas in 13 books, and these books were there weren't any references in these books because somehow there weren't any other books. He didn't have to refer to anything else because this is somehow, sort of mathematics was being born here. And if you look at mathematics being born in other countries and other cultures, you see the same sort of thing. The Chinese and the Indians and other places, mathematics appears and people have ideas and do calculations, but everything is kind of self-contained at the beginning. And that didn't stay like that forever. After the Renaissance, lots more people started doing mathematics, and people started having ideas that were somehow sufficiently important that other people were going to, they didn't need to regenerate them; they could just use them. So things began to pile up. I was told there was going to be. I'm supposed to be running to time. Oh, I see. It says 6:10. It just says 45. Oh, it started now. Thank you. So by the 1800s, things were beginning to pile up, and people were using things that other people had done. And so by 1900, we got some pretty juicy stuff. So, for example, one of the things we'd done was we'd proved the main theorems of global class field theory, this is a technical. I'm not going to be telling you what this theory says, but this was hard won. This was a non-trivial mathematical theorem, global class field theory, and the proofs were long, and they relied on things like Galois theory, which had been developed a few decades earlier, and other things as well, certain facts from algebraic number theory, which were quite hard to prove, and this is in some sense one of the main achievements of 18th century mathematics. This proof of the main theorems of global class field theory, and you might hope that in the 125 years since this theorem was proved, you might hope that mathematicians sort of looked at it and generalized it and simplified it and conceptualized it and abstracted it and sort of got to the core of what was going on. And you might hope that it somehow became sufficiently conceptually, you would hope that we would understand it sufficiently well that we could make it easy. And that hasn't happened. That didn't happen. We can now prove some far more general theorems, and our proofs are much slicker than the original ideas. We have, the advent of cohomology made it so that we could state theorems in far more conceptual and clear forms. But the proofs of the main theorems of global class field theory, I learnt them when I was a graduate student in Cambridge at an advanced graduate level class, and the proofs, they occupied an entire lecture series. So even now, we can't explain this theorem in a 1 hour lecture, comprehensible to undergraduates. This is a difficult proof, and that's where we were by 1900. So as you can imagine, things have got a lot worse since then. So by 2000, mathematicians had announced the proof of the classification of finite simple groups. In fact, they announced it in the 1980s. And then they retracted it, and then they announced it again because there was some misunderstanding, and then they announced it again in the early 2000s. And this is a gigantic proof, which has still not really been adequately documented in the literature. There is a proof in the literature somewhere, but it sort of involves reading sort of papers by hundreds of people, and you need an expert to sort of guide you through. So there's an attempt to make a second generation proof where sort of 13 or 14 volumes, big volumes, not like Euclid's book, big volumes are being written in an attempt to guide people through the proof of this theorem. And it's still not done, and it's gigantic. And it probably will get done quite soon. I was talking to one of the people that's involved with the project. Of course, it's been going for a very long time. But it's still, 20 years after it was announced, in some sense, it still hasn't been written down. So that's what mathematics looks like. So I've told you lots of facts. This is an opinion. In my opinion, mathematical ideas have become so complex that the traditional methods we have of writing them down are now struggling to cope. There's just something I can attempt to justify that opinion. So let me give you some more examples of what mathematics is like now. So there's a preprint server, archive.org, and mathematicians upload. When you've written something, before you submit it to a journal, you typically upload it to this mathematical preprint server. And I get an email from this website every day. And every day it tells me the 20 plus new theorems, 20 plus new articles in number theory, which have been uploaded in the past 24 hours. So these correspond, if you look at them all, there's hundreds of pages being added to the mathematical corpus every day. And that's just in number theory, which is one branch of mathematics. So that's the rate at which mathematics is expanding, or that's one way of, that's one measure of the rate. Individual paper, I mean, most of these papers are short, but it wouldn't surprise me if once a week you see a monster. It's not rare now to see 100-page papers. I collaborate with computer scientists now, and one of the things that really struck me as surprising was that I submitted a paper to a computer science conference proceedings, and I was told there was a maximum page limit of 16 pages. And I'd never seen that in mathematics. That was, of course, chaos if you told all mathematicians that 16 pages was now the max. So 100 or maybe even 200-page papers, these are not uncommon, with many, many references. And these things are sent to journals, and the journals send them to referees, and the referees are supposed to make some value judgment as to whether this paper should be published. But referees are now explicitly told, and have been for decades, that it's not their job to check all the details, right? Turns out it's the author's job. And the referee is supposed to make some value judgment as to whether the paper's good enough for the journal, and whether the ideas, whether the ideas explained in the paper sort of feel like they're strong enough to prove the main results of the paper. That's the sort of the thing that you make some judgment call as a referee, but you're not expected to check the details. And of course, you don't get paid for it either. So it's a sort of a funny system. And as you can imagine, it's not going to be quite as efficient. I don't know. There's some problem as far as, I think there's some problem. And then another weird consequence of mathematics becoming gigantic is that now means that we can't really teach what's going on to the undergraduates, because we have this view in mathematics that the way you run a mathematics degree is you get the students in from school, you tell them to forget everything they've learned, you do one intro to proof class, and then you tell them the axioms of the real numbers, and then off you go. You spend the first year developing proving all of the theorems in single variable calculus from first principles, and then you spend second year proving the theorems of multivariable calculus, and then the third year developing the theory of manifolds. And by that stage, you've just about got to the 1940s, and then they graduate. And so, and the same is true in algebra, and this is our final year group theory course is teaching people Sulov's theorems, which are probably 1930s. I can't remember. I should never have. Anyway, so it's quite, and we think this is normal. This is now normal. And I look at what we're teaching our undergraduates, and I look at what I learned when I was an undergraduate, and it's just the same. Hasn't moved on at all. Whereas one of my children went to university to study computer science, and in their final year, they were doing courses that were on topics that hadn't been invented when I was an undergraduate. They're doing stuff on sort of machine learning and neural networks and sort of modern. I mean, it's difficult. You can't really compare maths to computer science because computer science is a much newer subject. But there's something. This is odd, really. I don't know, but it's also what's happening. So there you go. That's where mathematics is. And now the question is this okay? Does mathematics have problems? And of course, I think that some of the things I've said, we're all used to it, but I think that some of the things I've said indicate that there are problems. But you talk to lots of other people, and they would argue that there's no problems at all. And so here's, our papers are sometimes incorrect. More often, they're not incorrect, but they're incomplete. You read things like, this is true and this is true, and so now clearly this is true, and you kind of try and work out why this is clear. And I've certainly had, about 10 years ago, I got an email from some random graduate student saying, I was reading one of your old papers, and you said this, and therefore clearly this. Could you explain exactly how you get from here to here? And I just read it, and I thought, I definitely knew this at some point. But, this paper was old. And it's just a clear indication that I'd not written enough information in that paper. But the paper got published. And as I say, I'm skeptical about whether the refereeing process is scaling. I know terrible things that I'm not going to indulge here. I'm not going to name any names, but I know important papers that just contain incorrect claims, and the experts all know they're incorrect. And there's some 8-page PDF that gets circulated between the experts that explain how to fix everything up. And somehow, my impression, I discovered one of these things myself. I was like, I can't follow this line at all. This looks wrong to me. And I asked somebody, and they said, oh, yeah. Have you not seen the erratum? The unpublished erratum, because the authors are too proud to admit they've made a mistake. But if you ask the right person, once you find the error, you get sent the erratum. So there's all, I don't know. But it's okay, because it's always been like that. And the historians of maths are quite happy to tell you that. They can tell you lots of things, that the nature of research, there's chaos at the boundary, because the boundary is the living part of mathematics, but all the things are happening and the ideas are sort of partly formed and are falling into place. And that's what mathematical research looks like. It always looked like this, and so it's okay that it still looks like this now. And this is why mathematicians don't think there's a problem, because we've all grown up knowing that in practice, this is what mathematics is done by humans, and so this has consequences. So as I say, and now I sort of step away and I look back at these things and think, is this actually okay? And if you're a mathematician, you can choose, right? But the point of the talk is, can we do better? Okay, so what's happening today? So people have been doing mathematical research for thousands of years, and for most of those years, technology was limited. But one big change in the 1950s, 1960s, mathematicians, at least those privileged enough to be at universities that could afford computers, mathematicians started getting access to these things that were superhuman at calculating. And they could do long, tedious calculations very accurately and quicker than humans. And that had some effect on mathematics, but actually had less than you might think. Less than you might think. You talk to mathematicians, and it's not difficult at all to find mathematicians who just never, they use computers to do sort of search and email and things like this, but and communication. But they don't use them to sort of help with their own research, because mathematics, a powerful computational tool is not the sort of thing that will help them. They're doing stuff that you can't compute, because everything's sort of intrinsically infinite dimensional and uncountable. And if you're doing that kind of mathematics, then a tool that can calculate very effectively might be less use than you might think. But somehow the point of this talk is that other things have happened in the last few years. There's computers are now being used in other ways, and these other ways can impinge upon mathematics. So computer as generator of mathematics, and computer as checker of mathematics. So these are different to computer as numerical calculator. So by a generator, is that annoying, that pointer? Let me move that pointer. So the large language model, ChatGPT and that sort of thing, is you can ask it to generate mathematics, and it will happily attempt to do so. And then there's another more technical tool that somehow didn't quite perhaps sort of get inserted into the public psyche in the same way, but is equally important in this talk, the computer-proof assistant, which I'll explain more about later. So now I'm going to talk about how these new tools interact with research mathematics today. And let me start with the language model. So this is ChatGPT, it's the first one, and then there's many, many other ones now. So these are systems which are easy to use because they understand human input, and they can they can write answers in English, and they work using something called next token prediction. So the way it works is that every stage the computer looks at, here's all the things the human said so far, and here's all the things that I've said so far, and now we've got to figure out what the next word is in this conversation. A token, let's just say token means word. I've got to figure out what the next word to say, and it uses a big database, if you like, in some sense, to generate a probability distribution as to what the next word should be in this sentence, and then it chooses randomly according to this probability distribution. And the amazing thing is it works, and it can generate sort of coherent. For a long time it didn't work, but then people people had good ideas, and now it works. So there's the language model, and general opinion with language models is that either they're going to save us or they're going to destroy us, or sort of anything in between. I'm not going to talk about where they're going in the future. I'm just focusing on where we are today and how good are they at mathematics today. I'm not making any predictions about the future here. So one thing that's clearly present is the hype machine. And these things that turn out, to make this database, to make this large table of real numbers, costs huge amounts of money. You have to solve a gigantic computational problem, and to use these things and to make these things is extremely expensive. And so it's essential for the tech companies to constantly be generating a lot of hype, claiming that these things are going to be brilliant at everything. And so you have to sort of try and strip away the hype and work out where we are, and where we are. Is that certainly these things have got good at solving international mathematical Olympiads. The International Mathematical Olympiad is a sort of an international competition for very smart high school students, so like 18 pre-university students. And these machines are getting good at that, and they're also getting good at guessing, not proving theorems, but guessing numerical answers to technical questions. So that's where we are, and then the hype machine says, well, if they can do that now, then within a few years' time, they're going to be better than all of us. And you have to decide yourselves as to whether that follows from what we have. But the truth today is that right now these things have never told us anything that we didn't know already. Basically, you take some Fields medalist that's spent 5 years working on a problem and they can't solve it. And then they could give it to a machine, and then the machine can't solve it either. That's where we are now. And who knows where we'll be in 5 years' time? But right now, these systems have never told us anything profound that we didn't know already. They've answered questions that we already knew how to answer. So they're not useless. You can brainstorm ideas with them, and they are good at solving you have some intermediate result that you can't quite figure out, and you type it into the machine, and the machine might be able to do it. But the big problem is they're still called hallucinations. They should really be called confabulations. The machines confidently make claims which are not true, and it turns out that it's quite difficult to eliminate. You can kind of understand that, right? You think about how it works. There's some probability distribution, and there's a 99.9% chance that it's going to say the right thing next, and there's a 0.1% chance it's going to say the wrong thing. And so, and then you use them a lot, and then it's going to make a wrong turn now and again. And the big issue with hallucinations is that that's what people want. Is that people don't want the system to say, I don't know. We test these systems, we give them data sets and say, solve the problems in this data set. And you remember what it's like when you do an exam. You do an exam, and if you don't know the answer to a question, then you can either skip it, or you could just write some nonsense and hope that the examiner is sick and tired of marking them and just gives you. And this is how we're testing these models. You don't lose marks for getting the wrong answer. You're better off having a guess. And the other issue is that humans want the models to sort of reinforce their ideas. So they will typically, if you ask a language model to give a proof of the Pythagorean theorem by induction, then it's unlikely to say that's not really possible. It's far more likely to have a good go at trying to prove Pythagoras' theorem by induction. It will generate some plausible-looking crap, and sort of that's unfortunately where we are. And of course, the big problem is that the moment you make one false claim, then your argument. The way mathematics work is that everything has to be true. You can't just you can't have mostly true and then one thing that's false. Like one thing that's not how mathematics works. It all has to be true. So that's language models. That's where we are with them. And then there's this more exotic thing, the computer proof assistant, that maybe many of you haven't really heard of. But the way this works is that mathematics can be thought of as a sort of a single-player logic puzzle game. So the idea is, you start off with the axioms of maths, and then the rules of logic. Those are the rules of the game, and the puzzles, the levels are theorem statements, and then you have to prove the theorems just using the rules of mathematics. And this is you can explain, you can write down precisely what the rules are, and you can teach those rules to a computer. But computers have got very good at board games recently. They've been superhuman at chess for many decades, and they're now pretty much superhuman at all board games, give or take. But the problem is, your board games you buy in shops tend to have finite boards because it would be a little bit inconvenient to have an. But mathematics, the simplest mathematical object is the counting numbers, which is an infinite thing. So that's what makes it so much more interesting. That's what makes mathematics much harder than chess. So what's an interactive theorem? So computer proof assistant and interactive theorem proof, they're the same thing. I'm going to call it ITP, interactive theorem prover. This is a piece of software that knows the rules of mathematics, and it can check. It can check your work. That's the idea. Unfortunately, there's a catch, though. These things, ITPs, each of them is a programming language. And you can check mathematics, but the mathematics has to be written in that language. And so Lean, Rock, and Isabelle are sort of the big three when it comes to interactive theorem provers and mathematics. These tools, actually, they're not a recent thing. They've existed for decades, but they were not sort of on the mathematician's radar for many years. They were being sort of designed and used by computer scientists, and the number of mathematician adopters were you sort of count them on the fingers of one hand, up until about 2020, when suddenly mathematicians started to pick up on the fact that what basically happened was that various work came out in the late 2010s that indicated that these systems were now good enough to understand modern mathematical research. And that woke the mathematicians up. Because somehow in the 1990s, they were just sort of proving that 2 add 2 is 4, or square root of 2 is irrational, that sort of thing. They were sort of, they were prototypes. But now they're good. And in particular, the lean theorem prover has got a lot of traction amongst mathematicians, and as a result of mathematicians getting involved, suddenly we're seeing recent work of Fields medalists. So Fields medalists they write their papers in natural language, but then mathematicians who've learned the software manually translate this stuff into the language of one of these systems, for example, lean, and then lean can check. Lean can check sort of serious modern research mathematics, and this is why mathematicians are suddenly waking up to these things. But the translation is currently essentially all being done manually. So that's what an interactive theorem prover is. And just the same, where are we now? Just like the language model, these things have told us nothing profound, which we didn't know already. So there was a deep blue moment in 1997 where a computer beat the human world chess champion. And a few years after that, it was quite clear that computer programs could beat every human at chess. So you could call this the deep blue moment when humans realized that computers were now superhuman when it came to chess. And that deep blue moment has not yet occurred with these technologies. They're engaging with research level mathematics, but they're most definitely not superhuman at this point. I'm not making any claims about what's going to happen next week, but at this point, these things are not superhuman. So there you go. That's something they have in common. That neither of them have changed the world yet. But there's also some very important differences between these two technologies, because language models they can write stuff autonomously. You give it a question and it can it can write stuff all by itself, and it will be mostly accurate, but not always accurate. Whereas these theorem provers, they can't write things by themselves. They just sit there waiting for some external source to type stuff into their language. But in terms of accuracy, they're superhuman. People have asked me about this, but I've been using these systems for 8 years, and basically every time the human says something and the computer says something else, every time the computer's been right. So I think it's not unreasonable to say that they have superhuman accuracy. And because basically the weakness of each one is the strength of the other one. And so, of course, you should put them together. So what do I mean by putting them together? It's not difficult to explain. If you take ChatGPT 2022, when it originally came out, if you asked it what 8 7s were, it would tell you that they were 56. But if you asked it to multiply 2 10-digit numbers together, it would get it wrong. It would give you a number of approximately the right size that began and ended with the right digits, and in the middle all the digits would just be made up. And you could say, actually, that's not, you've got that wrong. You'd say, oh, you're absolutely right. I'm very sorry. It's actually this, and it would just write another made-up number. And in it was good fun. In 2022, I'd give lectures about this sort of thing, and I would sort of show people live the fact that these things were really, really bad. There were certain questions that it was really, really bad at. But ChatGPT 2024, you can't do that anymore. Because what happens is it's wise to this. When you ask it a mathematical calculation question, next token prediction is not the way to answer. It's not the way to answer how to multiply two. There's an algorithm for multiplying 2 10-digit numbers together. The way to do it is to apply an algorithm, not guess what the next letter is in this sentence. And by 2024, OpenAI realized this, and now when you ask ChatGPT to multiply 2 10-digit numbers together, it doesn't do next token prediction. It simply knocks up a Python program and runs the Python program. The Python program multiplies the numbers together, It runs the program, and the program prints out the answer, and then ChatGPT reports the answer. And so now it gets it right. Now that's great. And so now let's not do calculations. Let's do proofs. I'm interested in proofs. What happens if you ask a language model to prove the Pythagorean theorem? It will just knock off a proof, no problem. With high probability, it will give you a highly accurate proof of the Pythagorean theorem because it's been trained on that. There are hundreds of proofs of Pythagoras' theorem on the internet. It's been trained on them all. You can just rattle off a proof. But if you ask it to resolve an unknown mathematical conjecture, it'll give it a go, probably. And it will, there will be gaps or errors because at the minute they're not capable of doing things that humans can't do. So if we can't do it, you can guarantee whether or not it says it's done it, it won't have done it. And so of course the analogy is, we've taught them Python. Why don't we teach them Lean? Why don't we enhance the model so that when you ask it a proving question, it writes Lean code. It comes up with an idea, then it translates that idea into Lean, and it runs that code in Lean, and almost certainly Lean will say this doesn't work, and the first error is here. And then that information gets fed back to the language model, and the language model says, oh, I see, yes, you're absolutely right. My code doesn't work. Let me try this modified code. And it goes back and forth with the theorem prover saying, no, here's the first mistake now, until eventually, if you're lucky, the theorem prover says, actually, yes, now this compiles. And once that's happened, then the language model then translates it back into English and reports back how it answered the problem. So if that could be done, then you have some system there that could potentially eliminate hallucinations in LLM output. And such an idea could extend well beyond mathematics, right? There would certainly be applications beyond mathematics. So that would be an interesting experiment. So this has been in the air for a couple of years, and I've always felt that there are sort of technical problems with this idea. And so I would highlight two major obstacles. And the first obstacle that I used to highlight is that there's an issue. The reason that LLMs can write Python code is because there's billions of lines of Python code on the internet. So you can just train on these billions of lines of Python code, and then you get very good at Python. But even if you take all of the Lean, Coq, Isabelle, and all the other systems, if you put them all together and you train on all of that stuff, firstly, that's like 10 languages, not one. But secondly, there's only millions of lines of code, maybe sort of 10, 20 million. So you're sort of a couple of orders of magnitude short. So there's not enough Lean code to train on. But actually, that objection seems to have disappeared now because the systems just get better and better all the time. And I've seen language models writing excellent Lean code. So the fact that there's only millions of lines of code somehow doesn't seem to be an issue anymore. The reason I think that is because sort of several companies have now independently made systems that can answer International Maths Olympiad problems in Lean. So these systems are writing Lean, so that's good. But I've got another objection, another obstacle, and this obstacle still remains. And the big problem with this other obstacle is that for the vast majority of modern mathematical research, these involve very sort of technical, complex modern mathematical objects that have not been explained to the theorem provers. So there are certain technical objects which are there, and certain technical theorems about these technical objects which have been formally checked by these systems. But there are many, many other modern mathematical definitions which are not in the database. So we're missing hundreds, probably thousands of definitions are missing. And the big problem, like you kind of think, well, I know how to solve this. Let's just get a language model to translate all these definitions into Lean or one of these systems. But the problem is when you start translating definitions, then there's no guardrails anymore, right? If you ask one of these systems to prove a theorem, and then it says it's proved a theorem, if you compile the code and it compiles, then the thing has proved a theorem. But a modular form is a function that satisfies about 10 axioms. And if you ask a language model to translate the definition of a modular form into Lean, and it's sort of something goes a bit wrong, and it sort of misses out one of the axioms, then you've got a definition that compiles, but it doesn't agree with the human definition. You see, the system can't check that. So I'm involved in 2 projects, both of which are attempts to sort of try and solve this problem. And the first one is a project funded by the EPSRC in the UK, whose goal is to formalize the Wiles and Taylor-Wiles papers to prove Fermat's last theorem. And you can kind of see, I'll show you the top. There, this is, this is just, there's Fermat's last theorem. You can sort of click on it and see. There it is. And that's in green, which means it's been proved modulo some other stuff, and this stuff in blue hasn't been proved. And these are sort of technical claims. So we sort of reduce, this small graph here reduces Fermat's last theorem to 2 very hard problems. And then there's another graph that reduces this hard problem to 3 very hard problems. And we're sort of slowly chopping Fermat's last theorem into smaller pieces. And now I've got to find my talk again. There it is. And one of the motivations I have for doing this project is that it's going to teach, it's going to force us to teach Lean's maths library, some of the definitions which are being used in modern number theory. And the second project has just been funded by Renaissance Philanthropy as part of its AI for Math program. Is we're going to be formalizing in Lean the statements of recent theorems in all the top maths journals. And the point of this, one of the points of this project is that now this will force us to teach Lean many of the definitions being used across modern mathematics. Because in my mind, this is a sort of serious bottleneck in where we are. So, coming to think about, where we are, how we're going to use technology, it seems to me that this is sort of an important problem, and I'm sort of trying to help solve it. So, as I say, I've suggested that there are several thousand missing definitions, but actually a few thousand is not a large number, especially if I can persuade other people that this is an important problem, and they want to work on it as well. And you could imagine humans and language models collaborating to solve this problem, really getting the definitions, the things that we need to start stating what we believe. You could imagine that in a couple of years we could have made real inroads into this. But actually there's one more serious obstacle that I hadn't mentioned yet. And that serious obstacle, if I click on this, this is Lean's maths library. This is Lean's maths library on GitHub, and this is the open pull requests. And there's 1,991. There's 2,000 pieces of mostly interesting looking mathematics that people want to put into the library, but that need careful human review. So basically, Lean's maths library is a victim of its own success. And for me, this is a big, people would, what have we got? Fourier transform, that's kind of important. There it is, 4 hours ago. Well, it doesn't work yet, yeah. And it doesn't work, and it also needs other work. So eventually we'll get Fourier transforms of L2 functions, but it could be months. It could be months before those things arrive. And for a long time, I was quite worried by this fact because I sort of couldn't see it scaling. But thanks to the generosity of Alex Gerko, the CEO of XTX, we might have a solution to this. So this is a secret website. It's going to be launched next week, so I won't tell you the URL because people are worried that they were going to. No, we don't want anyone. Maybe when they've stopped recording, I'll show you that. But this is the MathLib initiative, and one of their focus areas is responsive review cycles, under 1 week response time for 90% of review rounds. So those 2,000 pull requests are going to start dropping pretty darn quickly when this gets off the ground. And there you go. It's got a certain amount of funding, but there you go. You can click on support us as well. I wonder how I'm going to make that go. Well, maybe it doesn't matter. So, okay. Once we've got the definitions, we can start worrying about the theorems. And you see, this is what people really want. They want. How do we get superhuman immediately? Right? How do we just get a machine to magically prove the Riemann hypothesis for us? This is still science fiction. Right? In 5 years' time, it might not be, but right now, get a machine to magically prove an open problem is science fiction. But get a system to translate the human literature into Lean and thus check it and fill in all the gaps and find all the errors. It seems to me that this is now becoming an actual feasible. It will be difficult, but it will be feasible. It's fast becoming feasible. And once you have that, you have a new way for machines to think about all modern mathematics, and you kind of wonder whether that will help. And people are doing this already. There's a Californian startup, Math Inc. They've just announced their system. They've just announced they've formalized the prime number theorem, and the way it worked was that they took a human proof just written in normal English, broke the proof up into very small pieces, and then they got the machine to translate the pieces. And the machine would sometimes get stuck. It would say, I can't get from this line to the next line. So the humans would go back and add more details. And what I'm unclear about is what will happen. The prime number theorem is 100 years old. When we start doing modern research, will the systems just sort of ask us how to, will they get stuck on every line, or will they get better? And my gut feeling is that I'm generally an AI pessimist, but I'm sort of not pessimistic about this. So that's it. Last slide. Seems to me we have a choice. We can either just keep doing things the way they've always been, or we can attempt to upgrade the system. And upgrading won't be pain-free. It will cost time and money. But I think it's now becoming viable. And so now mathematics, the community will have to decide, is mostly right? Is it good enough? Or should we upgrade to definitely right? So thank you very much.